Hey guys, my name is Tensor. Welcome back to the Introduction to Elixir tutorial series. Today we're going to be closing out our control flow block of this tutorial series by talking about iterations and recursions, enums, comprehensions, tail call optimization, and a few other things. So first let's discuss how Elixir handles looping in general. In Elixir, looping is a lot different than what you would find in a mainstream language. Constructs like the while loop or the do while loop or even the for loop aren't really provided in Elixir, or at least they're not provided in the same way. That being said, it's pretty common to have some kind of looping inside of a programming language, so how do we go about doing it in Elixir? Looping is done via recursion. Now, to really sink our teeth into this concept, let's take a look at this function here called print. Now, the idea behind this function is that it will print the first n natural numbers, that is positive integers, and it will then print from n all the way down to 0. First, we have our first clause, and this matches on the value of 0. And if we get 0 into the print function, then we want to pass back a atom that just says OK. In our second clause, we have n, and of course n could be anything except for 0 based on how we've devised the pattern matching here. So in theory you could put negative numbers in here, but that would cause this program to loop on infinitely. If we take a look at the body of this function, you can see here that the function actually calls to itself by taking n, subtracting it by 1, and then calling back to print. And then afterwards it calls IO puts with n inside of it. And so let's say, for instance, we call print of 10. This is what we would get. We would get print of 10, it would print out 10, and then the recursive call would call print of 9, which would then print out 9, which would then call print of 8, and then this pattern would repeat until you get all the way down here to 0, where we would get back an atom. So we just say 10, 9, 8, 7, 6, etc., and then end with OK. Alright, so let's import this into our IEX terminal and then run it. And I'm going to run it with 20 inside of it. As you can see here, we get numbers from 20 all the way down to 1, and then we get back the atom of OK. This code demonstrates a basic way of doing a conditional loop, and we've used a multi-clause function to do this. The first clause is what stops the recursion, and then the second clause is what initiates the recursion. This is a general pattern that you'll find in recursive functions inside of Elixir. Now let's consider, for instance, a function wherein we want to take a list and then compute the sum of that list, and of course we're going to do this recursively. So for this example, our first clause needs to define where we want this recursion to end. And of course, because we're summing a list, our natural ending point is just when the list is empty. Then for our second clause, when we get a list that isn't empty, we can of course pull the list apart by taking out the head and the tail. So in this case, we're binding the head to H and then the tail to T, and then this allows us to handle each of the elements inside of the list individually. And so here you can see that we actually take the head out and then we add it to a recursive call to sum on the tail, which is the rest of the list, of course. So as an example, let's say we call sum on a list of 1 to 5. For our first iteration, the head will be 1, because the cons of this list is the first element, which is just 1. Then the tail will be 2 through 5. We take that head, 1, and we add it to a call to sum on the tail. So sum then is called on 2, 3, 4, and 5. In this case, the head for this list is 2, and then the tail is 3 through 5. So then we are adding 1 plus 2 plus sum of 3, 4, and 5. And then again we get to the head, which is 3, and then the tail, which is 4 and 5. So now we have 1 plus 2 plus 3 plus sum of 4 and 5. The head of this is then 4, and then the tail is just a list of 5. So then we get 1, 2, 3, 4, and then sum of 5. And the head for this list is, of course, 5. And then the tail is an empty list, and so we get 1 plus 2 plus 3 plus 4 plus 5 plus the sum of the empty list, which gives us back 0. And then that stops the recursion. And so we can go ahead and sum any list together inside of our sum function. So if I put in 1 through 10, we get back the sum, which is 55. Now it's important to understand how function calls work under the hood. When we call to a function, we do what's called a stack push, which then will therefore consume some memory. So when we have very deep recursion, this will potentially lead to a stack overflow that may crash the entire program because we're running out of memory. But this isn't necessarily a problem in Elixir because of what's called tail call optimization. Now, a tail call in the case of recursion is when a function calls to another function or itself as the last thing that the function does. And so in this case, calling a function doesn't result in the usual stack push. Instead, something more like a go-to or a jump statement happens. And so we don't actually have to allocate additional stack space before calling to the function, which in turn means that the tail call function consumes no additional memory. Tail calls are useful in any type of function, but they're especially useful inside of recursive functions. The function can run virtually forever without consuming additional memory. And so if I wanted to, I could define a function that loops forever by creating a function like this called loop forever, which then just calls itself. And of course, this function uses a tail call optimization because the last term inside of the function is just to call loop forever. To demonstrate this idea of tail call optimization, let's take a look at this example. So here we have a start function, which calls to a getNumber function, which then calls itself recursively to create a Fibonacci sequence. So inside of start, we have a timestamp that we get from OS system time, and we want to get it in seconds. Then we call to the getNumber function, and then we call for another timestamp, and then we can subtract these two timestamps to get the actual elapsed time that it took to execute the function, and then we can of course print it out. And we also want to of course print out the Fibonacci number that we got back from calling the getNumber function. Down in the getNumber function, we have 4 clauses. We have one that starts at 0, which gives us back 0. And then we have another one which starts at 1, which gives us back 1. Then we have a catch function to catch any number that is less than 0, because this would give us an error. With this one, we just want to pass back an error atom. Finally, we have the main logic of the getNumber function, which just takes in a number n, and then what it does is it calls itself recursively twice, one with n-1 and then the other one with n-2, and it adds these two together. Now the reason why this is not actually a tail call is because the last thing that this function is doing is adding these two functions together, because we need to get answers from these two calls. Alright, so now let's walk through this algorithm. So let's say we call getNumber 5. What does this actually calculate to? GetNumber 5 calls to getNumber n-1 and getNumber n-2. So we take 5, we subtract 1 from it, and we add getNumber 4 plus getNumber 3. We then want to take getNumber 4 and getNumber 3 and further break them down into our recursive calls. So getNumber 4 would give us back getNumber 3 plus getNumber 2. And then getNumber 3 would give us back getNumber 2 plus getNumber 1, which actually just gives us back 1 in accordance to this clause here. So then we can further break this down by breaking down getNumber 3 again. So it just gives us getNumber 2 plus getNumber 1, which again is just 1, so I can just replace this with 1. GetNumber 2 is just getNumber 1 plus getNumber 0, and so that gives us 1 plus 0, so getNumber 2 here is also 1 plus 0, and then the getNumber 2 here is again 1 plus 0. We also have another getNumber 2 right here, and we're adding that to this, so again it's another 1 plus 0. And then finally we have our get number 1 over here, which just gives us back 1 like that. So fib of 5 just gives us back 5. We can now use this definition of get number 5 to find get number 6 a lot faster. So we already know that get number 5 is going to give us back 5, and so all we really have to do is calculate get number 4, because get number 6 breaks down into get number 5 plus get number 4. And ultimately, get number 4 breaks down into get number 3 and then get number 2, which we already know is 1 plus 0. And get number 3 is just 1 plus 0 plus 1. And so the fib of 6 would give us back 8. I know that defining a function in terms of itself can be a bit confusing, but if you walk through it like we're doing here, it's actually fairly intuitive once you get a handle on it. Alright, so let's import this into our IEX terminal and see how long it takes for this function to calculate the Fibonacci of 40. Now if you look here, you can see we get back fib is, and then it gives us the number. And I'm not even going to try to say that number because it's got too many digits. But it took us 6 seconds to calculate this fib of 40. Now if we go ahead and implement tail call optimization into this getNumber function, you'll see that the amount of time it takes to calculate the Fibonacci of 40 goes down drastically. Alrighty, so let's take a look at what our new functions look like. We have 4 clauses for this getNumber function. The first one takes in n when n is less than 0, and again it returns an atom of error. Then the second one takes in n, and then it calls to getNumber of arity 3 with n as the first term, 1 and 0 as the second and third terms. Our first getNumber arity 3 function, if it receives 0 as the first term, it's going to then return the third argument of this function as the result. And then we have our main logic where we take in n, a variable called next, and then a variable called result, and then we call getNumber with n minus 1, next plus result, and then next. N is the number in the Fibonacci sequence that we want, so say we put in 40, n will be 40. Then the next is the next number in the sequence. So if we got up to Fibonacci 40, next would actually be populated with the Fibonacci of 41. Result is the Fibonacci number that we're currently at. So in this case, if we're still at Fibonacci 40, then result would be 40. Now if you think about it, when we're at Fibonacci of 0, 0 is the first term of the Fibonacci sequence, and 1 is the second term, and that's why we're putting them in here like this. So when we call fib of 0, we get back 0 as the result. And again, that's our stopping point for this recursive function. When n gets all the way down to 0, we get back our result. Let's first walk through calling getNumber 10, and that is the getNumber of arity 1 with 10 in it. This would then call getNumber 10, 1, and 0. We then want to follow the logic that we have here, so we take n, subtract it by 1, and that would give us 9. Then we take next and result, which would be 1 and 0. We add them together, which would give us 1, and then we have next, which is just 1. And so now we call getNumber with 9, 1, 1 inside of it, and then this would give us getNumber with 8, 2, 1, because remember we're subtracting 1 from 9. Then we're taking these two values, adding them together, which gives us 2. And then we're taking next, which is this 1 value, and putting it in here. This pattern then continues for 7 and 6. N minus 1 is 7. Then we have 2 plus 1, which gives us 3, and then 2, which is our next value. Then for 6, we have 5 and then 3. Then for 5, we have 8 and then 5. For 4, we have 13 and then 8. At n equals 3, we have 21 and 13. Then at n equals 2, we have 34 and then 21. And then finally, we get down to n equals 1, which gives us 55 and 34. and then n equals 0, which ends the recursion. And so this value here we don't really care about, even though it's just 89. And all we really care about is the 55 here. And so we end up passing that 55 back to the start function, which called this original function inside of it. With our new tail call optimized function, we can go ahead and call to playground start with 40 inside of it. That rather than taking 6 seconds to calculate the value, it took 0 seconds. And in fact, the performance boost is so radical that I can call to Fibonacci of 100,000 and it will still only take 0 seconds. You can see here we get back this rather large number for this value in the Fibonacci sequence, and then it says here that it took at the very least less than 1 second. Alrighty, so we've looked over recursion, we've looked over tail call optimizations. Now let's look at some of the built-in functions that Elixir gives us which use recursion inside of them. If you go into the enumeration module, you'll find quite a lot of functions that have recursion built into them, and that's because they deal with enumerable types. So as you can see here, we have this enum each function. We put in a list or a collection type that can be used as a enumeration, and then we apply a lambda function to it. In this case, we're just taking a value and then printing it out. And this enum each function is just going through our list and then printing out each of the values individually. This function is doing what's called iterating. So it's iterating through the list and then applying the function to each of the elements independently. This iteration under the hood is powered by recursion, since there is no other way to do loops or iteration in Elixir, but all of the complexity that comes with recursion is hidden from us by way of this function call. There are 3 primary functions that I really want you guys to understand inside of this enumeration module. The first one is the map function. Now the map function is very useful, especially when you want a one-to-one transformation of a list to another list. And so what this function does is it takes an enumerable and a lambda, and then it maps each element to another element. In this case, it's just taking each element of our initial list and then doubling them using our lambda. Another useful function is the filter function. Now the filter function takes in an enumerable, in this case a list, and a lambda, and then it only returns the elements from the enumerable that correspond with the lambda when the lambda returns true. So in this case, we're looking for values where the remainder of the value is equal to 1. In other words, we're looking for values that are odd, which are inside of our list, and so we get back 1, 3, and 5. Filter is extremely useful if you want very specific elements and you want to get them out of a map or out of a list or some type of collection. Now the last function that I really want you guys to keep in the back of your head is the reduce function. And the reduce function is probably the most useful function in the entire enum module. Reduce takes an enumerable as its first argument. Then the second argument is the initial value of what's called the accumulator, and the accumulator is what is actually computed incrementally. And then the final argument is the lambda that is called for each element. In this case, we're calling reduce on a list of 1 to 5. We're starting our accumulator at the value of 0, because we just want the sum of 1 to 5. And then our lambda function takes in 2 arguments. One is x and then the other one is y. And then we just add these 2 arguments together. So let's take a look at how this actually walks through everything. So first, let's start with 1 and 0. So this is our first iteration through our enumeration. So x equals 0 and then y equals 1. And then of course this gives us 1, because 1 plus 0 is 1. Then the next value of x is this value, which is our accumulator value. So x would equal 1, and then y is equal to the next value in our list. So we get y equals 2, and then these two added together would give us 3. Now our accumulator is equal to 3, and so we take that value, put it into x, and then y is equal to the next value in our list, which is 3, which gives us back 6. And then of course for our next iteration, we take 6, put it in for x, then y is the next value in our list, which is 4, we get back 10. And then finally, we get our value of 10, put it in for y, and then x equals 5, which gives us back 15. Now if we just move the initial accumulator up to 10, all that really happens is the initial x value becomes 10 like this, which then makes this 11. Then this becomes 11, which makes this 13. Then this becomes 13, which makes this 16. 16 makes this 20. And then 20 makes this 25 like that. And so that's all that's really going on behind the hood for these two reduce calls. Now let's look at another construct that exists that allows us to iterate and transform enumerables. And this construct is called a comprehension. Here's an example of a comprehension. So we say for x, where x is a value inside of our list between 1 and 3, do x times x. What this does is the comprehension will iterate through each element and then run the do end block. So the result is a list that contains all of the results returned by the do end block. In this case, it's just x times x. For 1, we have 1 times 1, which gives us back 1, then 2 times 2, which gives us 4, and then 3 times 3, which gives us 9. Comprehensions also have various other features that often make them elegant compared to enum-based iterations. For instance, it's possible to perform nested iteration over multiple collections. We can go ahead and say for x, where x is a list of 1 to 3, and y, where y is a list of 1 to 3, do create a tuple where the first term is x, the second term is y, and then the last term is x times y. So we get back a list filled with tuples where we're taking each of the values in our lists and iterating through them and then multiplying them together. And so if you look at the actual output here, you can see that the initial value here for the first 3 values that we got back is 1, which means that x is just 1. So x is at 1, then y is iterating from 1 to 3. Then we move up to x equals 2, and again, y iterates from 1 to 3. And then we have x equals 3, and then y equals 1 through 3. And so the iteration of the y variable is actually going faster and is actually nested inside of the iteration of the x variable. In a traditional language, this would actually look like this. So we'd have like a for loop with the x value, and say it's just iterating from 1 to 3, and then we'd have like a for loop with the y value. So for each loop of the x loop, we have 3 loops of the y loop, and then it just keeps doing that until the for loop of x ends. Our comprehension has just iterated through lists, but we can really use a comprehension to iterate through anything that is an enumerable. So as you can see here, we're using ranges instead of lists, and we have this other keyword here called into, which is allowing us to put the values here into a map. And so even though we're getting back tuples as our values, we're putting these into a map. The map comes back, and then the keys of the map is a tuple of x and y, and then the value is x times y. And so we could go ahead and bind this comprehension to a variable. Let's just call that variable table. And then we could recall a value by typing in the values for x and y. So say we want to find out what 8 times 9 is. We put in a tuple of 8, 9, and then we get back 72. Another thing to note is that this format here with the nested tuple is used to specify what we want to be the keys and what we want to be the values. We know, because this is nested like this, that we want the key to be a tuple and then the value to just be a normal integer. We could go even further with this comprehension if we want and add what's called a filter. So what we're doing here is saying, all right, we just want the values where x is less than y. So this filter now sort of works like a guard, or sort of like a enum filter, and that it only returns back values that satisfy this conditional in our block. Now, of course, if we go into our file here, you can see that we don't actually have to write comprehensions all on a single line like we did before, but the normal version of the comprehension just uses a normal do end block like this. So we can just have for x, where x is 1 through 3, and then we just have the do end block here, so we can have more than one line inside of the comprehension, and we can sort of work it like a normal block in Elixir. Alright guys, well I hope you enjoyed this tutorial. If you did, feel free to like and subscribe. If you have any questions or comments, feel free to leave them in the box below. And if you disliked this video, then by all means downvote it as much as you like. Have a good night.